Hello, in this lesson we are going to discuss the derivative of the function log base a of x. So this comes on the heels of doing the derivative of a to the x, and now we're inverting that function. So the first thing is, let's just define a function as simply that. Y is equal to log base a of x. Now if we write this in exponential form, well, this is the same thing, these two are the same thing. A to the y equals x. This is a little more useful for us. One, we know the derivative of some value to a power, an exponential function. And two, and obviously now we're seeing how useful number two is, we understand implicit differentiation. Implicit differentiation, for example, already allowed us to find derivatives of arc sine, arc cosine, arc tangent, and we were able to do those because rather than simply staring at this thing and saying I don't know the derivative, we write it like this. This is something we do know the derivative of. So this is, of course, why we're using implicit differentiation to find derivatives of inverse functions of things that we already have studied. So now we take the derivative of this. Remember, just pretend that it's a to some power I don't know. What is the derivative of that? Well, it's a to the power I don't know times natural log a. And the chain rule then comes in here also, because we have to multiply that by dy dx, since this power, if for example, side example here, if it was a to the 5x, this thing's derivative would be a to the 5x times natural log of a times 5, because the power is 5x instead of x. Okay, so that's simply the left side there. Now the derivative of x is 1. And we're going to solve for dy dx. So dy dx. And remember what y is. Just think about the fact that y is log base a of x. So we're trying to find the rate of change of log base a of x. And right now we're solving for dy dx, which again we will have found without ever having isolated y, I guess you can think. 1 over a to the y, natural log a. And that's just a little bit of a strange form because y is defined right there. So I'm just going to rewrite it as a to the log base a of x. I'm subbing, maybe I'll put that in a different color. I'm just replacing y with the green there. Now, a to the log base a of x, you might have to think about that for a second. But for example, let's come up with something that we do know. 2 to the log base 2 of 8. Well, log base 2 of 8 is 3. Then 2 to the third power would give us 8. Because what this thing is saying is effectively, this is the specific power I need to raise 2 to get 8. So when I raise 2 to that special power, I of course get 8. So a raised to the log base a of x, remember the green thing represents the following phrase. The special power I would need to raise a to in order to get x. So what is a raised to that special power? Well, of course, it's x. So there you have it. This then is the derivative of log base a of x is 1 over x times natural log of the base. Now let's do, starting to think that might be hard for you to see. Let's do natural log of x. So with natural log of x, dy dx, following that pattern, remember that natural log of x is really log base e of x. So the derivative of it says that it's 1 over x natural log of the base, which is e. That is 1, so the derivative of the natural log function, which is an important result, is 1 over x. So this is something you definitely want to take note of. Derivative of natural log of x is 1 over x. Okay, we'll do a couple examples. We'll do a natural log example, then we'll do a log base 10 example. But of course, these apply to any base. Okay, the function is equal to the natural log of x cubed plus 1. So now the derivative, maybe pause, give yourself a second to practice or work your way through it. Hopefully you've done that now. So we're going to do 1 over the argument and before you say, okay, done, remember that this argument is a function of x, not x. So think of this as yet another application of the chain rule. So f prime will be 3x squared over x cubed plus 1. But you might notice, of course, that there's no log base whatever attached to the denominator here. That's because it's really hidden there. Of course, we've shown in this little mini proof that log base e, of course, is 1, so we don't have a log on the denominator. Okay, next example. That's log base 10 of, let's see, 2 plus sine of x. Just checking my notes there. 2 plus. So give yourself a chance, see if you can take the derivative there. Hopefully you've already paused it and done so. You do 1 over the argument times natural log of the base times again chain rule, derivative of the argument, and if you want to make that look a little prettier, of course, just throw the cosine right in the numerator. I'm not going to do that, but of course, you know, we could do any number of things here. Let's just say, for example, you wanted to find a horizontal tangent line to, where is there a horizontal tangent line to this function? Well, we know the derivative is that. The derivative tells us the slope of the tangent line. So we could set this guy equal to 0 and then solve from there. And you might think, oh my God, I've never seen anything like that. But remember that when any fraction is equal to 0, the numerator must equal 0. So offline here we could say cos of x must equal 0, and you could solve for the 2 places that happens, or I guess infinitely many places depending on the domain that you're considering. And then also, it's of course a good thing always to consider what the domain of the function is and all that kind of thing. But anyway, point being, we've now found the derivative of y equals log base a of x. We established that derivative by inverting the function to say if that's true, then a to the y is equal to x. We already knew about a power rule. I'm sorry, not a power rule, that was incorrect. We already knew about an exponential function rule. The power rule is when the variable is the base. So we already knew about our exponential function rule where we can take the derivative. So we took the derivative of this while using our new leverage of implicit differentiation, and we found the derivative of that logarithm. We then applied that to the specific logarithm of the natural log, aka log base e, and then we did a couple of examples. So you'll have lots more opportunity to practice this. Just take your time and email me with questions.